Good evening, GCC College Algebra students. Continuing in Chapter 12 tonight, Chapter 12.6, we've been looking at systems of equations, and boy, that matrix stuff, that sure does get confusing and frustrating. And like I said in previous lessons, you can actually take a whole class in matrix mathematics and do a lot of the regular stuff we do using matrices. Computer programming. Matrices are a big part of computer programming as well. If you go on to do things with computer programming, you will be using matrices. Computers tend to think in matrix forms with zeros and ones as entries. The language is called binary. But here we're going to take a look at looking at systems of equations, but we're going to completely change gears here. We're going to look at nonlinear equations. Well, what does that mean? Nonlinear means that they're not just nice, well-behaved lines. When we had two lines, we only had three possibilities. The lines could intersect in one place, or maybe parallel lines, they don't intersect anywhere. Or we could have two lines that intersect everywhere, really the same line. Well, if we start adding non-linear stuff, some weird things will begin to happen. For example, consider the idea of a parabola, and remember the parabola is a U-shaped thing, and a line. If I take a parabola and a line and I put them on the same graph, there's three possibilities. And let's just kind of talk about the concepts here. So I'm just going to draw three sketches of what could happen given a line and a parabola. Well, I could have a parabola right here and a line right there, and of course I've got no points of intersection there. I could have a parabola right here and a line right there where I get one point of intersection, or I could have a parabola right here and a line right there and I get 2 points of intersection. Now think about this for a minute. When we had two lines, there was another possibility of an infinite number of solutions where really basically the two lines were the same line. Is that a possibility here? Is it possible to have an infinite number of solutions given a parabola and a line? And the answer is no, they're not the same model. My possibilities are no solutions, one solution, or two solutions. Okay, let's do an example of a system of equations that uses a parabola and a line. All right, so for my first example, I'm going to use the line 3x minus y equals negative 2. That's a line. That's a nice, well-behaved line. I could subtract 3x's, divide by negative, put it in y equals mx plus b. Notice that the y's and the x's only have powers of 1. Nothing weird, no square roots or powers or anything else going on. It's ax plus by equals c. It's a line in standard form. And then 2x squared minus y equals 0. That is a parabola. If I subtract the 2x squared, divide by negative, I get y equals negative, or y equals 2x squared, which is a nice, well-behaved parabola. So I've got a line and a parabola, and I want to solve the system. All right, so when we solve the system, we can do it graphically, although we're not going to do it graphically by hand. Have your calculators nearby, because after we solve this one algebraically, we're going to do it on the calculator as well. Doing this algebraically, solving systems when I've got a line and something other than a line, or maybe both of them are non-lines, we're going to think about it the two different symbolic methods. The good news here is we cannot use matrices. Not only are we not going to use matrices, but we can't. The only time we can use matrices is if they're all first degree. So matrices is off the table. Don't worry about matrices. No matrices at all. Now, I'm sure that makes everybody very happy here. So when I'm looking at solving this system, and I'm thinking about, well, how could I solve it nice and quick and easy? I'm going to solve it by substitution. I'm going to take the parabola here, 2x squared minus y equals 0, subtract the 2x squared from both sides, divide by negative, and I get y equals 2x squared. Now I'm going to take the line which is 3x minus y equals negative 2. And I know what y is. Y is 2x squared. I'm going to take that and I'm going to substitute it in there for y and solve. So when I substitute it in, I get the new equation, 3x minus y, which is 2x squared, equals negative 2. Now I'm going to solve this equation. All right, and of course when I solve this equation, I'm going to find the x value at the solutions. And as we know, it's possible that there are no solutions here, that this line and the parabola don't ever actually intersect anywhere. It is possible that they intersect in one and only one place, but it's also possible they intersect in two different places. All right, let's solve this equation. 3x minus 2x squared equals negative 2. I'm going to subtract the 3x over, add 2x squared over, write it in descending order, and I get this. Subtract the 3x, there it is. Add the 2x squared, there it is. The negative 2, there it is. Solving this equation. It's a quadratic in standard form. My methods for solving this, I can always crank it through quadratic formula, but does it factor? And I think if we take a closer look at this, we will see that it actually does factor. If I think about factoring this by splitting the middle term, so I've got 2 times negative 2 is negative 4. Remember the first times the last, a times c. That's the key number in splitting the middle term. Can I think of two things that multiply together to give me negative 4 and add up to give me negative 3? How about negative 4 and 1? So I can split the middle term. I'm going to split this middle term. And I'm going to get 0 equals 2x squared minus 4x plus x minus 2. So the negative 3 became a negative 4x and a positive 1. Group the first two terms together, the second two terms together. This is all from our factoring chapter, isn't it? Out of the first group, it looks like I can factor out a 2x, and I'm left with x minus 2. Out of this, I can't factor anything out, x minus 2. But the x minus 2's are the same. I can factor those out. X minus 2, what am I left with? 2x plus 1. Got to have that 1 there. So when I multiply it back in, I've got that term. Set each factor equal to 0. Oh, I'm running out of space on that here. Let me continue it here. And I'm going to get x minus 2 equals 0, x equals 2. 2x plus 1 equals 0. Subtract 1, divide by 2. And I get x equals 2 and x equals negative 1/2. All right, what's happening here? What does this mean? This means that the parabola and the line are going to intersect in two different places. This is the x value of the first point of intersection. This is the x value of the second point of intersection. This isn't a point here. These are both x values. What I need to do is find the corresponding y values. All right, so here we go. So first, when x equals 2, I need to find the y value. Well, I'm going to plug it back into one of my original equations. It doesn't matter which one. I'm going to use the line. The line, remember, was 3x minus y equals negative 2. And I'm going to substitute this x value in there and solve for y. And I get 3 times 2 minus y equals negative 2. 6 minus y equals negative 2. Negative y equals, subtract 6 from both sides, negative 8. Divide, y equals 8. Oh gosh, I'm right down there at the bottom, aren't I? All right, so let's see what happens when x is equal to negative 1/2. Again, I'm going to plug it into 3x minus y equals negative 2. I'm going to substitute this value of x into the original equation for x and find the corresponding y value. 3 times negative 1/2 minus y is negative 2. Negative 3/2 minus y is negative 2. Add 3/2 to both sides. What is negative 2 plus 3/2? we should know that it's negative 1/2, but if we don't, we can look at the calculator here. So let's see, I've got negative 2 plus 3/2, negative 0.5, or negative 1/2, divide, and oops, I'm off the screen, aren't I? And I get y equals positive 1/2. In other words, when x is 2, y is 8. I get the point 2/8. When x is negative 1/2, y is positive 1/2. I get the point negative 1/2, positive 1/2. So I think that these are the points of my intersection. So now, so here it is. We solved it algebraically. Now let's actually do it on the calculator. So on the calculator, let's go back to the original system here. Let me see if I can put the original system down here at the bottom. There it is. Trying to keep the work and the solutions. Trying to get it all on one page. Here's where we solved for the y values when we had the x values. Here's the original system. This is what I want to focus in on right here. The original system of equations. I want to graph this system. Now, I need to get them into y equals form to graph them. I'm going to need to do a little bit of work here. All right, so let's take the original system. I'm just going to copy the original system down again, which was 3x minus y equals negative 2, and 2x squared minus y is 0. I want to graph them, so I want to get them both y equals something. So for this equation, 2x squared minus y equals 0, subtract negative y equals negative 2x squared, divide by negative. That looks familiar. I think we did that originally, didn't we? So that one's in y equals mx plus b form, or not mx plus b, but y equals something form. 3x minus y equals negative 2, subtract the 3x's. Negative y equals negative 3x minus 2, divide by negative, y equals 3x plus 2. So these are the two lines that I'm going to graph. One is a parabola and the other is a line. All right, so I go to my y equals, clear out the junk that's in there, and here we go. So I'm going to graph the line 2x squared in y1, there it is, and 3x plus 2, 3x plus 2 in y2. Entering in my calculator, I'm going to go to Zoom Standard Viewing Window. The standard viewing window goes from negative 10 to 10 and negative 10 to 10. All right, so here comes the parabola. There it is. Here comes the line. There it is. And we can see that the parabola and the line have 2 points of intersection. 2 points. So now let's use the calculator to find those 2 points. Now, Casio users, you're going to hit gsolve intersect. TI users, second trace, which is our calculate button, down to the option of intersect, which is number 5. Now my little cursor, my pins, I want to drop it to the left of my first point of intersection. So I'm going to use my back button until I'm at the left of that first point that I want. And then I'm going to hit the enter arrow 1, 2, 3 times. And it gives me, at the bottom, it tells me negative 0.5, comma, 0.5, which of course is negative 1/2, 1/2. That was one of the points that we found. Look back at the original solutions that we did. That was one of the points. Now let's find that other point. Casio users, if you're on the gsolve already, just hit the right arrow and it'll jump right over there. TI users, we're going to have to identify that point. Second trace, which is the calculate button. Go down to number 5, intersect. And this time I want to drop my pins just to the left of this other point of intersection I'm interested in. I've got it just to the left of the intersection. Hit enter, hit enter, hit enter. And it tells me the point 2, 8. So the calculator found the exact same 2 points we did. Of course, the calculator did it much faster and quicker and easier. So there it is, confirmed exactly what we thought. The 2 points. We did it algebraically and graphically. Believe it or not, algebraically is going to be the easier way to do a lot of these. Let's consider a whole different system here for a moment. Let's consider something like a parabola, which we know is this U shape here, and a circle. a circle looks like this. Now, if I put these two together, what are the possibilities here? And there are actually 5 possibilities. Five possibilities. Let's take a look at them. We'll do the first 3 here, and then I'll get another piece of paper and we'll do the next 3. So first, is it possible that there are no points of intersection? Yes. For example, I could have the parabola here and the circle there. No points of intersection. Is it possible to have one and only one? Yes. I could have the parabola here, and I could have the circle here. 1 point of intersection. Is it possible to have 2 points of intersection? Yes. I could have the circle here and the parabola there. And I could get 2 points of intersection. So 0, 1, 2. Is it possible to have exactly 3 points of intersection? Yes. For example, if I had the circle here and I had a parabola that comes down and touches and then goes, whoops, that's not very good. Oh dear, I don't like that diagram. Let me try this one again. If I've got the circle here and I've got a parabola that comes down and touches and does that. So now I've got 1, 2, 3 points of intersection. And then finally there's one more possibility here. I could have a circle here and a parabola that looks like this. And I get 1, 2, 3, 4 points of intersection. So with a circle and a parabola, I've got 5 possibilities. No solution, 1 and only 1, 2, 3, or 4 possible solutions. So you can guess that algebraically this gets kind of crazy. Weirdly enough, it's easier to solve them algebraically than graphically. Sometimes graphing these things can be very awkward and very difficult. All right, let's take a look at a system here. So for this particular system, I'm going to use a circle, x squared plus y squared equals 13. We should remember the equation of a circle from way back when. The other one is a conic section. The other one's going to be a parabola. I'm sorry. X squared minus y equals 7. So I've got a parabola and a circle, just like we talked about in the examples. So I know that there are either no possibilities, no solutions, no points in common, or 1 or 2 or 3 or 4. Just looking at this and staring at this, I've got no idea. I could put this in standard form, subtract the x squared, divide by a negative, and I get y equals x squared minus 7. How would I solve this one for y, a circle? This one would be difficult to solve for y to plug into my calculator. Okay? But algebraically, so let's talk about solving the system here. This is a system of nonlinear equations. I've got a circle and a parabola, and I want to solve the system algebraically. Now, don't overconfuse this. Don't overthink it. Just look at it, and if I want to solve this one by substitution or elimination, well, I could solve this for x squared by adding the y, and then when I know what x squared is, I can plug it in there. So if I take this equation, x squared minus y equals 7, subtract the x squared, divide everything by a negative, and then I take my second equation, or my first really, the other one, and let's see, if that's y, do I want to plug that in there? If I plug that in there, oh gosh, look what's going to happen. X squared plus y squared. I don't want to do that. Oh no, this is going to get, this is messy. That's the, nope. Don't want to do that. I don't want to do that. That's not a good idea. I'm going to get x to the fourths and all sorts of crazy stuff going on. I don't want to do that. I don't want to do that. Let's do something different. Let's do something a little different. All right, so let's take this first equation, x squared minus y equals 7. Solve it for x squared. Add y to both sides. Now take the other equation, x squared plus y squared equals 13. And I know what x squared is. I'm going to take that and plug it in for x squared. And I'm going to get y plus 7 plus y squared equals 13. I like that. That's a lot nicer and easier. So I'm doing it by substitution, but the classic way of doing substitution, solving for y and plugging it in, gives me a horrible thing. I don't want to do that. That's no good. But I solve for x squared and plug it in for x squared. X squared is y plus 7. X squared plus y plus 7 plus y squared. This is the equation I want to solve. Take a closer look at it. You should recognize this as a quadratic. All right, here we go. So I need to solve y plus 7 plus y squared equals 13. Let's subtract 13 from both sides and write it in descending order. Y squared plus y, 7 minus 13 is negative 6 equals 0. So I subtracted 13 from both sides, wrote it in descending order. I need to solve this quadratic. Well, it's a nice, well-behaved quadratic. I can solve it well, can I solve it by factoring? Is this factorable? Can I think of two things that multiply together to give me negative 6, add up to give me positive 1? Hey, this is factorable. Y plus 3, y minus 2. Set each factor equal to 0. Y plus 3 equals 0. Y is negative 3. Y minus 2 equals 0. Y equals positive 2. This kind of feels like our first example, where I seem to get two solutions. I get that y could equal negative 3 or y could equal 2. So it seems like at first, and notice I'm being very careful to say that it seems like, but it definitely seems like I'm getting two solutions here. I know the y values at the solutions. I need to find the corresponding x values at the solutions. All right, here we go. So let's see what happens when y is negative 3. Let me see, my blue pen seems to be dying. Let me see if I can find another one. When y equals negative 3, I need to plug that back into one of my original equations. Does it matter which equation? No, not at all. I could use the line or the parabola. The parabola was x squared minus y equals 7. So I'm going to plug that in here. So I'm going to take this y value, substitute it into one of my original equations. I'm using the parabola here, and I'm going to solve. Over here, when y equals 2, I'm going to take that y value, substitute it into the original equation to find the corresponding x values. So I found the y values, right? By solving this, I found the y values. Now I need to go back and find the corresponding x values. All right, here we go. So x squared minus negative 3 equals 7. X squared plus 3 equals 7. Subtract 3 from both sides. X squared equals 4. Take the square root, and I get x equals plus or minus 2. When y is negative 3, x could be 2 or negative 2. What does that mean? There's actually two solutions here. I've got 2 comma negative 3 and negative 2 comma negative 3. When y is negative 3, x's could be 2 or negative 2. I'm getting two solutions over here, just in this one side by itself. What about over here? X squared minus 2 equals 7. Add 2 to both sides. X squared equals 9. Take the square root. X could equal plus or minus 3. I'm getting two different solutions of x for that solution of y. In other words, 3 comma 2 and negative 3 comma 2. When y is 2, x could be 3 or negative 3. There's another 2 solutions over there. Ladies and gentlemen, this parabola and circle have 4 solutions, and there they are. At first we thought there was only going to be 2, but for each of the y values we found, there were 2 corresponding x values. For each of the y values we found, here was negative 3, there were 2 different x values. For the y value of 2, there was 2 different x values. Now notice the numbers came out to be very nice and well behaved here. Is that always going to be the case? And I wish I could say yeah, but I'm not going to lie to you. No, a lot of times these problems, they turn out to be horrible answers, just awful type of problems here, and very difficult answers. All right, let's take a look at one more example of a nonlinear system. And in this system, I'm going to give you, we're going to have x squared minus y squared equals 4, and y equals x squared. Now we know that that's a nice, well-behaved parabola, y equals x squared. As a matter of fact, that's the parent function of parabolas. What is that? X squared minus y squared equals 4? If this was plus, it would be a circle, but it's minus. It's something called a hyperbola. Weird shape, hyperbola. We'll spend some time with the hyperbolas and circles, ellipses in the next class, in the 182 or 187 class, depending on which way you go. Not really important. I just want to solve the system here. And this is another one where they're both second-degree equations, so my possibilities are no solutions, 1 solution, 2 solutions, 3 solutions, or like we saw in that last problem, 4 solutions. All right, so let's go ahead and solve this system here. So let's see. What do I want to do? Well, look, y is equal to x squared. If y is equal to x squared, can't I just plug that in here? If y equals x squared, and that's x squared, can't I just plug the y in there and create a whole new equation of y minus y squared is 4? All I did was, given the fact that y is equal to x squared, if y equals x squared and there's an x squared, I just plugged in y. All right, let's get this in standard form. I'm going to add y squareds to both sides, subtract y. And as I take a look at this equation, I want to solve this equation here. Let's see, what are the solutions to this equation? Can I think of 2 things that multiply together to give me 4 and add up to give me negative 1? No, this is not factorable. I can't factor this one. So how are we going to solve it? Yeah, it's going to have to be quadratic formula. Remember, the quadratic formula says negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so substituting in, y equals negative b, which is negative 1, plus or minus the square root of b, which is negative 1 squared, minus 4 times my a value of 1 times my c value of 4 all over 2 times my a value of 1. So I get y equals negative 1 is 1, plus or minus the square root of, let's see, that's 1 squared is 1, minus 16 all over 2 times 1, which is 2. Well, I'm squishing everything together, aren't I? Wait, let me take a closer look at this. Y equals 1 plus or minus the square root of negative 15 over 2. Oh, wait a minute. Did I do this quadratic formula right? What just happened here? Take a closer look. This problem comes to a screeching halt. The square root of negative 15. Does the square root of negative 15 exist? Oh, I know, you're thinking about using i's, but don't lose sight of the big picture here. This is not real. This is not a real number here. Well, what does that mean in the scope of this problem? Then this is not real. This answer here is not real, which means there are no y values. More specifically, there are no y values where these two things intersect. This hyperbola and this parabola, no y values exist for intersection. So what does that mean? No solutions. These two things never intersect. This would be one of those examples of a system of a parabola and a hyperbola that actually never really intersect, because I got the square root of a negative number. And you can't have the square root of a negative number, so there's no solutions here. So watch out for the no solutions one. The homework's not so bad. There's certainly a lot more in this particular topic that you'll cover in the next class. You'll probably notice we only did the first half of 12.6, and that's all the curriculum states for this class. So I want you to do the homework in 12.6, which starts on page 934, and I want you to do problems 5 through 15 odd. That's 6 problems, 6 systems. Think about substitution and elimination as your methods of doing it. You can also graph them if you want. It says graph them and then solve to find the point of intersection. So in the note, let's take a look at what the textbook says here for a moment, because I just want to make sure we understand it. It says, for problems 5 through 24, and I've circled the ones I want you to do, graph each equation of the system and then solve the system to find the point of intersection. I don't care if you graph it or not. You don't have to bother graphing it. If you don't want to graph it, don't graph it. Just solve them all algebraically. Just like we did in the examples that I did. So solve them all algebraically. Show me the work. The answers are in the back of the book. But if you just put the answers down and you don't do any of the work, you will not get any credit. You must show me the work to get credit. And when you're done with the assignment, email completed assignment to me. And remember, since we're not doing any unit tests anymore, each of these graded assignments combine to give me a test grade. If you look at your grade book, each of the assignments is in there. There's like 10 assignments per chapter. Each one's worth 10 points. So that's up to 100 points. That's going to be your test grade, basically. So do all the work. Make it look really good. Don't just copy answers out of the back of the book. You won't get any credit for that. If you've got any questions, shoot me an email. Gosh, guys, I'm inundated with emails. Please be patient with me trying to get back to you on emails. I'm getting hundreds every day. I'm trying to plow through them and grade stuff and get it entered. Please be patient with me. We do have the semester has been extended a week, so we'll have a little bit of extra time to get stuff done. If you need more time, if you're watching this message, this lesson later than the date that it's going to be posted, which is going to be on Monday the 27th, if you're watching it much after Monday the 27th and you're falling behind, make sure you shoot me an email and let me know. I think GCC is going to be pretty flexible about getting grades in and giving students a little bit extra time to complete the work here. All right, guys, good luck. Got any questions? Email me. Thanks, and I'll talk to you again soon. Bye.